So let's say we have a wall and a pin joint at the wall and a rigid body here, and then I'm going to make a little more room. What? No, this is the next stuff. This is statically indeterminate systems. And then let's say there's a cable here and a cable here connected to the ceiling. We're going to assume that this thing is rigid. Those cables, because they're a lot thinner, a lot less material, are going to deform a lot more than that body is. Okay, so this thing's rigid. And let's say there's a downward force at the end of 5,000 newtons. Let's say this is 0.6 meters and this is 0.4 meters. And let's say that these cables have an effective cross-sectional area of 0.01 meters squared. And a Young's modulus of 200 times 10 to the 9th pascals. First of all, what does that effective area thing mean? So cables are, it's not the same as a solid metal bar of that same thickness because it's strands of metal that are wrapped around each other. So a lot of that area inside the shape, like if you just measured the area by taking the radius of the cable, you'd be measuring a lot of air in there. And so the effective area is the area that's made out of metal. Okay, so you wouldn't get that by measuring the outer diameter exactly. And we want to know what are the tensions in the cables. All right, well, first thing we do is the statics, but you can see that this is going to be statically indeterminate because you could take either one of those two cables away and the thing would still be in static equilibrium until the cable broke. But so if you have a setup where you could take something away from the problem and the problem is still in static equilibrium, then clearly this is statically indeterminate. Statics isn't going to give us the answer to this. Okay, but let's do the statics first because that's going to give us at least one equation that's going to be useful in solving this. So free body diagram, and we're going to isolate the beam. There's an unknown force here, call that R, and then there's a tension here, T1, and a tension here, T2. And I didn't give a weight, so I guess we're ignoring that. And then there's a downward force of 5,000 newtons. Then Newton's second law says Rx, Ry plus 0 T1 plus 0 T2 plus 0 negative 5,000 is equal to zeros. So Rx is equal to 0, we know that. And then Ry plus T1 plus T2 is equal to 5,000. Call that equation star. And now mathematically you can see that it's statically indeterminate. We've done everything. Well, that's not true. We haven't done everything yet. So let's go to the moment equation. About point, let's choose this left endpoint. There's no moment produced by R. The moment arm for that tension T1 is 0.6. And would that rotation be clockwise or counterclockwise? Counter, so it's positive. Same with T2, and the moment arm for that is 1. And then the moment arm for the 5,000 is also 1. And that one's going the other way, so that's going to be negative. And these add up to 0. So we have 0.6 T1 plus T2 is equal to 5,000. We can't solve either of these. So I'll call this equation star. This is 2 star. And how many variables do we have? 1, 2, 3. 2 equations. So it's statically indeterminate. We're going to have to figure out something, some restriction on the motion. Okay, so what's the restriction on the motion that we're looking for here? Look at this problem and see if you can think what we're going to use.
It's not going to go into the wall.
That's true, but we let's see, it's not going to go into the wall. That's really close. So we're not going to, I guess we're going to assume that in a way. We're also going to assume that it doesn't go up or down the wall. And so, yeah, our assumption is that this point of the rigid body stays exactly put, and that this is rigid. And so as these deform, we're going to get this thing, the endpoints of these 2 cables following a line. Like if you did a big deformation, it would be like this, you know what I mean? It's always going to make a line from this point and this point through the hinge. That was not clear wording at all, but you know what I'm talking about? Yeah. No. What it's going to be is that there has to be, so the deltas of these 2 cables have to make a triangle that goes, through that hinge. And so they can only deform in a certain ratio. Okay. So the constraint so if this is the initial position, the deformed position has to be this, where this is going to be delta 1, this is going to be delta 2. This is a right triangle. Now, if you really did a finite rotation of this bar, this would not be a right angle. Okay, because this, if it's rigid, this has the same length as this, right? And so this would be an isosceles triangle. This angle would be the same as this. But we're talking about, vanishingly small changes in angle. That's part of our expectation that deformations are small. And so we can approximate this as a right triangle, and it's going to make the math a lot easier. Okay, so what does this say? This is a right angle, and this is a right angle. This length is 0.6, and this length is 1. And so what we're requiring is that delta 1 over 6 is equal to delta 2 over 1. That's saying that, that angle is some theta. And for this little triangle here and this big triangle here, the tangent of that angle has to be the same. Those have to be similar triangles. Okay, so delta 1 has to be equal to 0.6 of delta 2. And now we're going to use the relationship between the tensions in the cable and the deformations. So delta 1 is equal to the tension in cable 1 times the length of cable 1, so whatever those lengths are. We're talking about the undeformed length of cable 1, so this is L. We don't have to know what that is. That's going to start out the same for both of them, and it's going to cancel out. Divided by EA. That's the same for both of them. And delta 2 is equal to T2 times L over EA. And so all of this together we can write as E1L over EA is equal to 0.6 T2L over EA. We can cancel a bunch of this stuff. And we see that T1 minus 0.6 T2 is equal to 0. And that's equation 3 star. Any questions about that? Okay, so now we have 3 equations for 3 unknowns. And the variables are T1, T2, and RY. So I'll just substitute 0.6 T2 in for T1. So I'll sub 3 star into 1 and 2. And equation 1 becomes, equation 1 star becomes RY plus 1.6 T2 is equal to 5,000. So this is, let me rewrite these as, so substitute 3 star into 1 star to 2 star. And equation 2 says 0.6 times 0.6 T2 plus T2 is equal to 5,000. So 1.36 T2 is equal to 5,000. So T2, what's 5,000 divided by 1.36? Say it again. 0.47 newtons. And then RY, what do you get for that? 882.35. And then T1 using equation 3 star. 2,205.88. Okay, so what we got is, because of the positions of these two cables, which one is closer to the end, which one is closer to the hinge, even though they're the same material and the same area, most of the force is going to be taken up by this cable at the end. Less is going to be taken up by that one. And that's because as this thing deforms in a straight line down like this one is always being forced to stretch more than this one.